Hello and welcome to the next part of the pathfinding tour. So last time we got our A-star pathfinding system up and running. We're getting some pretty good performance there with it, and we're testing it over large distances, so it was working really well. What we're going to be doing this time is we're going to take a look at how we can make that faster again, and also how we can improve some of the interfaces to it to make it a bit more flexible, a bit more usable across different scenarios that we might be running into. So first thing we're going to focus on is performance. So last time we were testing for the path length we were looking at, we were getting about 600 milliseconds for the distance. So pretty large distance, 30,000 iterations, 600-ish milliseconds. So we're going to look at how we can make that faster. And one of the things we're going to focus on is the container we use for the open list. So at the moment, we're just using a regular list. So we're actually going to change what we use here for this. Now, important thing with the changes we're about to make, we will hit a point very early on with these changes where our code compiles. We can't test yet until we make a bunch of other key changes after that, because if we do, we'll actually have things slower initially. Because what we're going to do is we're going to change our list to something called a sorted set. Now, sorted set is quite rapid, and it's quite rapid because it maintains the data in a sorted form at all times, but it has a number of very specific constraints in terms of how that data looks and how we work with it. So for a sorted set, the items must be unique, and the cost of an item can't change once it's been added in. So we need to look at some changes to how we manage and work with our costs. So we're going to get those things updated as well before we do any testing. So I don't actually need my initialization of G and H costs to max value, so I'm going to get rid of that. The other thing that must change is here in OpenNode, I need to set the costs before I open this. It's really important. We set up the costs, then we open it. And down here where I go and update it, because the cost of something can't change while it is in that list, what I have to do is open list, remove this node, and then do an open list add of that node. So I remove it, update its cost, insert it back into the thing. If I changed its cost before trying to remove it, it would struggle to remove it because it wouldn't be able to find it. So really important to make sure we remove it, then change the cost, then add it back in. Now, one of the things that becomes really simple is this, where we were searching. Nope. We just return openlist.min. So that's the first set of changes that we make there for this. Now, with our open list, we need to give it a way of being able to support, do that sorting, to do that process of knowing which things go before which other things. So to do that, we're going to create an open list comparer, and this implements iComparer with path data node. And this has a function in it, int compare, and then we have path data node, node 1, path data node, node 2. So how this works is we return one of three values. -1 means that node 1 goes before node 2. +1 means node 1 goes after node 2, and 0 means they're the same position. So what we can then do is, we're going to need our pathfinding context. So we're going to need linked context. And then what we'll do is, let's store our node 1 f cost, not left-hand side, node 1 f, linked context, get f cost, node 1, do the same thing for node 2. We retrieve that, get the f cost for node 2. Then we just compare these. So, node 1f If you are less than node 2f, we return -1, signaling that node 1 goes before node 2. Otherwise, if node 1f is greater than node 2f, we return 1. Now, rather than just returning 0 at this point, because we kind of need to handle the scenario of, okay, they could have equal f costs, but they might still actually be different nodes. We only want to return 0 when it's a case of, yep, these are absolutely definitely the exact same node. Otherwise, we want to give it a way of still being able to sort things in that set. So one of the things that we can do in that scenario is we could also check G costs, but we still need a fundamental way of saying, is this exactly the same? So I think the final thing what I would do is return node 1 unique ID compared to node 2 unique ID. So we just set it up so we've got a final bit of a comparison thing there. Then, well, we need a way to get our linked context in. So we're going to have pathfinding context, which will be able to be passed in to our constructor. So open list comparer. This will be a linked context. And we just set that up. So that's good. Then the way we use this is rather than initializing this here, what we do is after we set up our context, we go open list as a new sorted set, and we give it our comparer. And we give that the pathfinding context. So that's good. We've linked this up. It's using the sorted set. We also want to chuck in a couple of extra things to speed up general comparison things with our nodes. So we can say that our path data node implements system IEquatable. And that's going to imply a couple of functions we need to set up. We're also going to set up our equals function. So this is going to be one of the key ones we have to set up. And this just takes in any object. But we need a public bool equals, and that's put in general bits. Autocomplete being a little too over the top there. So the only thing the interface requires us to implement is this version. But we will have our common one here. We'll actually implement equals object as path data node. Now that means other could be null if what we've compared this against was something that's not a path data node. So first we check that other is not equal to null, and then we can just compare the unique IDs because we know that they're consistently unique, so we can just compare that. So that looks good. For get hash code, well, we want a fast thing we can use here. And again, our unique ID is the ideal one to use. We can just grab its hash code and use that. And then the final things I'll set up is a public static bool operator, path data node, left-hand side, and our right-hand side one. So these just return our equality comparer. Default equals LHS and RHS. And then the last little bit it needs, as soon as we implement the equality operator, we have to actually implement the inequality operator as well. But the inequality one is really simple. The easiest way to do this is you just do a return and you not LHS equals RHS. Saves us duplicating code. And so that looks pretty good. We've set up our nodes, so some quick methods for comparison there. We've set up our sorted set. So we've got that will be running instead for our processes here. So let's check and see. We know what our performance was before. Let's see what it is now. So we'll run, and 222 milliseconds, so a third of the time. So pretty consistently, that's showing a pretty good saving. And that's over quite a lengthy path here. 30,000 iterations, 200 odd milliseconds. I'm pretty happy with that. That's going to be giving us good performance. So, okay, we've improved the performance. That's great. Let's improve our tool set a little bit for this. And what I want to be able to do is I'm going to actually set up a little script here. And this I'll call Pathfind Tester. And the Pathfind Tester, I'll actually move my little debug things I had here for this stuff. It's going to get moved over to Pathfind Tester. And this, just so that we're doing this in an area that makes sense. Because then we're having to go directly to our pathfinding manager. So it'd be again a case of pathfinding manager instance request path. So all that will work largely as it did before. It'll just mean that we've got things moved over to a dedicated test object. And it's really handy to have these kind of tester objects and dedicated test scripts. I'd recommend keeping it to being dedicated test scripts. Makes it just a little bit more reliable. So humanoid 1 by 1. So we'll just confirm that that is still working before we go any further. And we can see, yep, it's still working. Okay, so I've got my setup for being able to request a path, which is good. But I want to have a little bit of stuff in terms of being able to control the bit of a budget for it. So we don't want to have it that our path can just run for as many iterations as it needs. We want to actually have a budget for it. So what I want to sort of set up with this is some configurations here in terms of budgets. So I'm going to have a serializable class, system.serializable, public class, and I'll call this pathfinding config. And I'm going to, so I think a reasonable way of setting up the budget is per distance, having a amount of nodes we're allowed to do for that. So node budget per cell. I might say 20. So for path, if the diagonal for a path is 100 cells, that means we have a budget of 2,000 for it. We might need to adjust this, but this will be a decent starting point. The other thing I'm going to have here then is we'll make this just system.serializable. Pathfinding config, synchronous config, because I want to be able to support synchronous and asynchronous pathfinds, and we want to have potentially different budgets for those. So let's set this up. Oops, it should be serialized field. We'll set this up so that we have this budget being actually followed. So the way we would use this budget is when we go to request a path down here, we would get end node grid position minus start node grid position multiplied by, and we'll need to get our configurations, in this case synchronous config, node budget per cell, but we don't use that. We use magnitude. So we'll set that in the context. So int node budget is equal to this. That looks decent. So our magnitude there is going to, because grid position, when we do magnitude on that, it is actually going to give us back a float. So we will do a mathf seal. This is one where I would definitely round up. So that gives us our budget, and I'm going to make it that that's something we have to provide in here as well. So our pathfinding context, int iteration budget, and we'll store this. And so have public int iteration budget set. We'll default to 0. So we'll just store this over, because then we can actually check that. And I'll rename that to iteration budget. So we're calculating our budget. And then, so we increment the iterations after every time we do get best node. So what I would be checking here is, and I'll do this in case we've just reached the destination, I'll check this afterwards. So I'd be saying f context, and f our num iterations is greater than or equal to iteration budget, log error, reached iteration budget of, and be useful to actually say what the budget is, and we return null. Reached our total budget. And I might log out what this budget is, just so we can see. So budget. And that'll allow us to work out if we need to tweak and adjust the configuration. So once we've got that where we're happy with roughly the budget, then we'll set up some stuff where we've got dedicated synchronous and asynchronous interfaces. So that reached the iteration budget, and that also exposed here. This needs to be checking f path. It's not equal to null. So if it actually found the path. So, okay, 8,000 wasn't enough. So that's something where we want to look at, okay, we know 8,000 wasn't enough. We know it's typically hitting about 30,000. So that means we need this to be about sort of four times what it currently is. So maybe we can go for 80. And it might be a case where this is the thing of like, yep, no, this is just too long a path, but that seems all right. So we're using a budget of 3,300 for that. If I grab the start marker and bring the start marker much, much closer, just so we can see, okay, over short ranges, because maybe we need it to be a little bit variable. So we'll test over a short range. So again, you know, that's pretty reasonable. That we could potentially go for a sort of different budget there. This would be one where maybe long paths we use an asynchronous pathfind with a more generous budget. And we keep synchronous ones to a very low budget. Could be a good way of doing this. So, okay, that looks pretty good. We've got our budget. I'm happy with how that's working out. And now what I want to do is I want to set up some better interfaces for this. I want to make it much, much sort of cleaner interfaces. And in particular, what I want to be able to do is get us set up for being able to have synchronous versus asynchronous pathfinds. So I'm going to make it that we have some new interfaces. So I want to think about this. I want to have a request path synchronous. Now there's some key things we're always going to need. There's key things here that just have to actually be there. Now, in terms of return values, it would be nice to know why it failed. So I think I want to set up an enum that I'll move to the top in a bit, but public enum e pathfind result. We've got a few different scenarios. So we have, because we have failed to find start or start invalid, end invalid, no, or different areas, or unlinked areas is a better term. Unlinked areas, no path found, budget exhausted. This could actually be maybe rather than result, the status. The result works. So no path found, budget exhausted, path found. So then I want to have this being something that is returned. So I'm going to change our request path function here to be doing that. And so that then means these ones start returning different values. So start invalid. Actually, that'd be no path data. No path data. So this means we're giving back a lot more information in terms of why things are going wrong, which is always really important. So end invalid, linked, means we can diagnose problems a lot better. We'll sort out the finding of path. That's going to return path found. Then when we exceed the budget, you can say budget exhausted. And then here we would return saying no path found. So that's good. We've got a much better set of things there, which is great. Now, in terms of sort of our setup stuff here, there's a lot of things that are pretty much common. All of this, whether it's a synchronous or an asynchronous pathfind, we would be doing the same thing. So this is something where I'd be inclined to set this up as ePathfind result, prepare pathfind. And that looks pretty good. I might make it that it can, I'll let it return the result. And I'll make it that it has our context here. So out pathfinding context. I'll also make it that the configuration is something it passes in. So it passes in the configuration, which I might bring that to the front. So it passes in the configuration. It's going to need to pass in all of these as well. So these a little bit neater. So we're just getting all of our interfaces nicely organized so that for everyone else using this, it's going to be a really clean interface. That's the goal. So, okay, that looks good. We create the context. Configuration, we just use the configuration that's passed in. And in terms of result here, we'd have an intermediate one of context prepared, because then we can just return that down here. So that's good. Now, context will set to null if we haven't actually processed anything, which is good. So what this would mean is we would do prepare for pathfind here. Prepare pathfind. We give this the synchronous config. We give it our UID, our start, our end, calculate cost, and then we need to have our pathfinding context. And what we would say is if result is not equal to ePathfind result, context prepared, then we just return the result at that point. So prepare the pathfind. Otherwise, we're going to assume, for now, I'm just going to put no path found. But, so we've got our setup stuff. And this we're checking, so context failed to be set up. So that's good. We've got our context, everything with that's all good. For our calculate cost, that would actually be a really handy thing just to store in the actual context itself. There's no reason we can't just store calculate cost within our actual context. So that's something where what I would be doing for that. So we can put calculate cost in here. So we would have, when we create it, calculate cost, which means we need to be storing that. So the idea is just that we bundle essentially all of the key bits into our setups here. So we're going to store this. And that will be an internal thing that it stores. This gets passed in as well when we instantiate this. So we can assign that over. So that looks good. Now, this is one where for the context, I would be inclined just to make that public rather than have a wrapping function. I don't think we need to have a wrapping function for it. But then this becomes pathfinding context, out, list, path data node, path. Doesn't need to be public. We'll set that path to null, just that it's being populated. Now, that means our context, we want to be able to check the end node in the context. So this is going to push more stuff into that context, but that's okay. Same with the path data. So context.pathData. We're going to need then here, when we've found that path, well, rather than it being actually having to set up a separate variable, we'll just be able to do that. So that looks good. Have context.pathData, so we're just moving more stuff into the context, which is going to simplify things a lot for us. So context.calculate cost. Because the advantage with this is once we've got more stuff in there, then that's going to set us up for being able to distribute this over multiple frames, which is a big part of the goal for this. So then we're also going to have in here public path data node, end node, get private set, and a public path data. I might change that to linked path data. Private set. And these are again things that we will pass these in for when we initialize this. So we'll pass in end node and the linked path data. Just going to make it really easy for us working with things, because then when we switch to some being asynchronous, that's going to be really, really straightforward for us being able to do that. So linked path data is equal to linked path data. That's a path data node. So down here where we were checking context path data, that changes to linked. That looks good. When we set up the context, we just need to provide our end node and our path data. So far, pretty good. We've got all of those updated and connected. And then this, we want it to output the path. So the final bit here is, this would actually be perform pathfind synchronous. So we would, in this one, return that. We give it the context and we give it our path. So we'll grab this for the found path, and we'll make this part of synchronous function, and we'll then be able to say found path just to be out. And then in this case, we need to do found path is equal to null. So that looks good. That'll use the synchronous config, so it's giving us a better interface immediately. And then what we do here is request path synchronous, and we get the result. And we also can then say out path, where path we set up here. So a list of path data nodes as path. So list of path data node. So it just gives us a nicer interface. So we've got our synchronous interface. It'll use that synchronous config with its particular budgets. And then we'll set up our asynchronous one. So we've got that able to be working as well. So we'll test this, because we just want to be continually testing, making sure things are working. So that's good. Synchronous one is working. Now let's set up our asynchronous one. So the idea behind the asynchronous one is it's going to do a little bit of work each frame. So that means budget-wise, we want to have public int iterations per tick, which I'm going to set that as 1. But we will have, we've got our synchronous config, and then we will have asynchronous config. And our asynchronous config, so if we think about it, 30,000 iterations, if we did 300 a frame, it would take 100 frames. We could probably do 3,000 a frame, and then it would take 10. So I reckon about 3,000 for the asynchronous. So its budget, I'm going to make it the synchronous's budget. I'm going to drop that to 50. Asynchronous gets a larger budget, but it can do those over multiple ticks. And I'm going to say it can have 1,000 one there. And I might actually change that. That really should actually be iteration budget per cell is a better name for it. So, okay, cool. Our asynchronous one is going to be an interesting one. So public ePathfind result, quest path, asynchronous. Well, a lot of this stuff is going to be the same, except it's going to need to get a context. So out, and actually what we could do is we could have it that it gets a context, Could also have it that it runs a function when it's done. There's a lot of different options that we've got there. We'll look at different things we could do in a moment. But the first chunk of stuff that it does is actually the same. This prepare part is all identical. It won't be finding a path, but so that's the first part of it is all identical. It's exactly the same, except it uses the asynchronous config. Now that context, that actually is something we want to pass back. So we want to give it the pathfinding context. And there's kind of different ways we could do this. It depends on who we give responsibility for the ticking to. So if the pathfinding manager has responsibility for ticking, then we don't necessarily need to give that context back. We could just have a function that gets run when it's complete. If the receiver of it is responsible for ticking, or the initiator of the path, then it kind of needs that context. So I think in terms of setup here, probably the best approach is going to be if the pathfinding manager has that responsibility for the context. So I am going to give it the ability to track these contexts. So I'm going to say list pathfinding context, pathfinds in progress, or asynchronous pathfinds. Asynchronous pathfinds is a new list of these. So I'm then going to add. So assuming that's been successful, then it's going to go, hey, asynchronous pathfinds, add this context. That means we need another state here of pathfinding in progress. Or pathfinding, yeah, pathfinding in progress works. So we can return pathfind result, pathfinding in progress. Now we need to provide a function that it can run when it's done, when it's found that path. So I want to have a system.action. So it's going to have two things. I think it needs a list of path data nodes, which will be the path, and that pathfind result on complete. So that on complete function is going to be run then when it actually successfully finds that path. So, okay, that looks good. We've got that set up. What we would then be doing is our context on complete is equal to on complete. So we need to store this in our pathfinding context as well. So similar to this one, we'll have public and that. So, okay, our pathfind result, we're going to move that up so it's more broadly accessible because we need it to be. So that's good, we've got that widely accessible. So then our pathfinding needs to tick these. So what it's going to do is in update, it'll go for index is 0, index is less than, and we have our asynchronous pathfinds. Count. Then what we want to do is context, retrieve that. Now we've got perform pathfind asynchronous, which will provide that context to, and we'll check our result. So if that result is anything other than pathfinding in progress, then we can invoke that on complete function. Now this will potentially get back a path as well, so we'd be able to have a list of path data nodes, path. And we'll set that up here like this. So if the result was anything other than pathfinding in progress, then we would say, well, context on complete, we invoke it, we give it the path, we give it the result, and then we're going to remove that context. So asynchronous pathfinds remove at 0, and we update the index just so we don't skip over another one. So we're going to tick all of the pathfinds in progress. Tick the pathfinding. Was it successful? Was the pathfind successful? So now we need our perform pathfind asynchronous, which is going to look very similar to our synchronous one. And I think we can actually get these so that they are working essentially the same. I think we can make it that this is going to be able to be used by both, just by having some configuration there on our context. So we're going to have both of them referring to the same thing, because the key thing is we need a set number of iterations to stop at. So we want int num iterations is equal to 0. We increment num iterations. What we would do is we would say if num iterations is greater than context, well, iteration per frame budget. If it is, then what we do is we would say, okay, return ePathfinder result, pathfinding in progress. So we've reached our limit for this frame. So this is something that we just store in the context. So we don't actually need too much different for our asynchronous version. So this ends up getting set up here. Int. We use the exact same setup we've got here. This going to change to iteration budget total. So iteration budget total and int iteration budget per frame, just so we're clear with the purpose of it. So that's our total one, and then we'll have our per frame one. Iteration budget per frame is equal to that. So it's good. We just need to change then where we're doing our setup stuff, and we will have all of our bits up and running. So it's an iteration per frame budget. There we go. Should actually have the naming of these consistent. So let's make it that these are actually nicely consistent. So, okay, we update our initialization of our context here. So there's not too much we need to do. That's in terms of with this. So we have our node budget. Well, we also have, based on the configuration we were given, our iteration per tick. And then we just need to update this to iteration budget per frame. Now we'll need to tweak these values a little bit. So our node budget for asynchronous will be 100. That can be 50. Now our iterations per tick for the synchronous one, we want that to essentially be as large as it possibly can be, or -1 to turn it off is a feasible option as well there. So we could be checking if that is greater than 0 and we actually have a budget, then we check. So, okay, that's good. Let's see how that actually looks. So this is doing a synchronous pathfind. Well, let's switch this to an asynchronous one. So this is going to be testing synchronous. So I'm going to move this into a separate function for doing that. So void test synchronous. Just want to keep that because that's a useful thing to keep. But then we're going to queue off an asynchronous one. So this I'm going to rename sync pathfind timer, because I want to also have then a system diagnostics stopwatch for an async pathfind timer. And so what we will do is we'll go pathfinding manager instance quest path asynchronous. So again, we need to provide these key bits of info. Once we've provided those, we also need to give it an onComplete function. So we're going to set up a void on async pathfind complete list path data node path and ePathfind result. So this can run on async pathfind complete. So we'll queue the pathfind up. We'll start our timer. Then at this point, we will stop it. So this one, when we debug log out, we'll say sync pathfind. And we will also log out the other one, but we'll log it out with a different set of data, essentially, or a different color. So we've stopped it. We'll log out async pathfind, log out the value of the timer, and these, we'll make these cyan, and we will offset these a little bit as well. Vector 3.forward, just so that they're shifted a tiny bit. So that looks good. That should mean that we have both our synchronous and asynchronous pathfinding, one for if we've got potentially really long, slow pathfinds we're doing, and one for things that we know should be really quite quick. So let's test and see how this is working. So we'll run this. Run. So we reached our iteration budget for the synchronous, which we expect. And our asynchronous one finished after 2,700 milliseconds, which we expect, like it was intended to be something that would be running over multiple frames. And the key thing is that it did. And we can then adjust the budget for it. So, okay, what if we gave it a larger budget per tick? We could give it 1,500, say. So with that, our async one finishes a little bit quicker. But so this gives us a key thing that we can use of synchronous one, has a much lower budget, so it's going to fail out for when it's a really long pathfind. But we have alternatives with our async one that are going to be much faster for it being able to use. And in terms of they can run in the background and we get told when they're done. So it means we can start to split up our logic based upon things that are essential and things that are, that we need quick answers to, and things that we can wait a bit of time for. So that's something where it gives our behaviors a bit more flexibility in what they're doing there, which is really, really handy. Cool, so we've got a really good setup now with our pathfinding. We've done a bunch of performance optimization so that when we're doing those pathfinds, we can get results a lot quicker. So we use that sorted set. We saw a couple of the key things we need to be very, very cautious of when we're working with sorted set to ensure that we actually do get a performance improvement and not make the performance worse. We also saw then how we can set up stuff so that we have asynchronous pathfind support and so that we have budgets in there, so that even in cases where if we do mess something up and a pathfind's going to take a really long time, that we can actually sort it out in terms of it has a cap, it will actually end. And we created an asynchronous version for if we've got really long, expensive pathfinds, we can do them in the background and we'll just get told when they're completed. And we'll get given the path and the result for it. So it makes it a lot more flexible in terms of the interfaces we can set up for it. So I hope you've found this helpful. And if you're looking for the code for this project, I have put the code up on GitHub. That's available there with the code for all of these projects. And with all of these, you're able to use that code for any of your own projects, whether those are commercial or non-commercial ones. You're free to be using any of that code there. And if you have found the video helpful, please do chuck in a like and subscribe. It's something that really does help out the channel. It's really appreciated. If you've got questions, chuck in a comment below. And if you're looking for other ways to support the channel, I do have a Patreon, and the link for that's in the description below. Bye.